All right, suppose we are being asked to compute the total amount of work needed to lift a 1.6 pound, 20-foot rope to the top of a building. What we do to analyze this, first thing I would do, and there are a couple of different ways of analyzing this, is first calculate that this rope weighs 0.08 pounds per foot. And then I'm going to represent this with a variable x, which represents the amount of rope that's already been pulled up. And how I develop my work function. I first develop my force function for how much weight am I pulling up at any one time. Well, so let's think about if we pulled out X number of feet right here, the amount of rope I have at any given time left to pull up is 20 minus X, and that amount of rope weighs 0.08 times the amount of feet of the rope, which is 20 minus X right here. And the way that I would think about this, so given this is my force function, again with the X representation above, is that we move that little piece of rope just a little bit, and then we have a little bit less rope to deal with. This gives this bigger function of the integral of 0.08 times 20 minus X, and then each of those are going to move just this infinitesimal much. So this is my displacement, and this would be my force. And then obviously, given my representation of X above, this would go from 0 to 20. The interesting thing about this is that when you calculate this out, and I won't show those calculations, what it ends up with is giving us, it takes 16 foot-pounds of total work. The thing that came to my mind was, that's interesting. If you thought about all in one group, if you were to do the work of lifting this rope, it would take 1.6 pounds times 20, which would be twice as much of this. So again, think about this problem. I'm going to adjust it real fast. Is say, if instead we had a string, let's say like a fishing line that was weighed nearly nothing or negligible, and we took that same rope that we had, balled it up here the bottom of this, and took our little thin, weighing nothing string here, and we pulled all of that rope up, all up in one heave, the work being done would be that 1.6 pounds times the 20 feet. Again, our force times our displacement. The interesting thing with the problem that we just dealt with is that every time you actually pull up, if you're using the rope to pull itself up, it gets shorter each time, and that's the reason for having this function right here. The question that comes to mind is, why is this end up being basically half the amount of work of pulling all of that rope up by itself?
So the question is this: why is the work required to pull up the rope, again using the rope to pull itself up, half of the work required to lift the entire rope, again with some imaginary non-force bearing object? And I mean, a corollary to this is this always the case? Is the question that I posed. And here, kind of mathematically below, is this question. Like, will this always work like this? Especially, let's just say, in the case of ropes or things like this. And the question, as I looked into it, is yes, it always is the same. And what we're going to do is use the same logic that, well, at least as the story goes, that Gauss as a child schoolboy did to add all the numbers up to from 1 to 100 in an amazingly quick fashion. What Gauss realized right away was that if he took the numbers, again the summation of 1 to 100, and laid it next to each other and did it twice in this way, he quickly realized what you would get in this is you get these pairs of 101. That every pairing here, if you went this forwards and backwards, you'd get each of these is 101. And obviously, if you look at the number of pairs there are 100. So you could multiply that value of 101 by 100, and then all you need to do is divide it by 2, because now we're doing twice the amount, to quickly find this summation. And what this has given us is this, in sigma notation, is this summation of I equals 1 to n of just I, always can be calculated with n times n plus 1 over 2. And above is a quick little informal proof of that logic right there. Well, in doing some investigation, I found that you could do the same kind of thinking with this problem to prove that, yes, every single time you do this with this same rope, it will always be half the force it takes to move the entire rope in one effort all the way up. So this actually is true. And here's my effort to prove to show you why this works. To analyze this question, what I was thinking of was looking at an approximation of this summation. Now again, the integral above is describing these infinitesimal moves where your dx, your delta x, goes to 0 as n goes to infinity. But let's make it much simpler and just think of if our n, our number of segments here in this case, were 20, our delta x would be 1. And so then each case here, we'd be calculating the work completed. We'd take 20 feet here, and we'd multiply it by our 0.08 times 20. We'd do it again to that 19, then the 18, all the way down to 2, 1, and then 0, which wouldn't do much. And then we'd multiply it by the displacement of each of those, which is 1 foot. Again, obviously, this multiplication of 1 wouldn't do much, so we can just get rid of that here. So that would be an approximation for this. And again, just in doing it with an n equal to 20, this value above actually approximates that with n going to infinity to get this exact value that we developed with integrals. Well, we look at that and we get that approximation. But now, to use the Gauss way of thinking about this, what if we did this twice? What if we did 2 sets of this work? So now we have 2 sets of these ropes of the same increments. Now that what I'm calculating again would be an approximation for twice the amount of work. I do it once and then I do it again. I calculate those values. But let's look at this. If we take these sections of rope and we interact them with the first set of work that we did, here's what. What we would are 20-foot ropes. We have 20 of them, so our force would be this rate per foot times the number of feet. So this is for each rope. By the way, this is obviously the weight of the entire rope originally, but we do this 20 times. So this would simplify down to the weight of one rope times 20 of them, but then divided by 2. This is exactly the same as what we were thinking was occurring up here, and it's showing that that is. And again, this is approximation, but this generalizes to show that you can calculate the amount of work of this rope by simply multiplying the length of this rope, or the weight of this rope, by the length it has to travel and dividing by 2 to find the overall work. And in general, again, the difference between hauling up that rope the entire way versus pulling it up by an imaginary string all the way up, it takes half the amount of work as it would here as all the work that it would take to pull that rope up in one haul.